Energy is an ability to do work, and it can be transferred from one object to another. So you can have an object that has a lot of ability to do work. It can lose that ability, but another object must gain that ability. You can't create or destroy energy. So we talked about all that in the last video. Now let's talk about how energy actually gets transferred. And I said something in the last video which maybe was not clear at the time, but we're going to look at in a little more detail now. Let's take the example that we were working at, which is a cylinder that's full of gas molecules. And I'm going to push the piston in on the gas. Now that's doing work. I am pushing on the piston, so I'm going to be losing energy. But where does the energy go? The energy is going to go into the gas as the piston slams against these maybe slower moving molecules. It'll make them move fast. So the molecules that are right under the piston head are going to get whacked, and they are going to move a lot faster. They're going to fan out into the rest of the gas, collide with those gas molecules, and pretty soon, when I have the piston pushed all the way in, those gas molecules that are in there are going to be moving a lot faster, because the kinetic energy of the piston has been transferred into the energy of the molecules. Now we've talked about, in the gas law chapter, we talked about how temperature is tied to molecular speed. So the faster the molecules move, the higher the temperature is going to be. So this is a hotter gas. It'll have faster moving molecules, and so higher kinetic energy. The kinetic energy came from the piston. This is an example of energy transfer by work. And I said that this was an orderly transfer, in that these iron atoms, say this was an iron piston, they stay in place in the piston pretty much, and they move in an orderly fashion, and they cause more random motion in the gas as they move along. But you have orderly motion that initiates the energy transfer. So the piston sliding in initiates the energy transfer. This is a molecular level view of what work would look like, doing work on a gas. Now you can see this process happening if you're pumping a bicycle pump, one of those tube pumps that you carry on a bicycle. As you pump, you're going to notice that the aluminum tube gets hot, and that's your energy that is heating the gas inside the tube and making the tube hot. Now you can also have random motion transfer energy. So suppose instead of a piston we have a wall, where we have a lot of fast moving molecules here. And they're moving in random directions maybe. And on the other side of the wall we have some molecules that are not moving very much at all. Now this would be a high temperature side because it has high average kinetic energy. And this side would be low temperature because it has low average kinetic energy. So temperature is a hotness-coldness property that is tied to the average kinetic energy of the molecules. So I got a hot gas here and a cold gas here, and let's take the wall away. What's going to happen when you take down the wall? Some of these molecules that are zipping around over on the hot side are going to hit molecules on the colder side. And after a little while, all the molecules, this is where the wall used to be, all of the molecules are going to be moving at pretty much the same average speed. So they're going to transfer some of their kinetic energy via collisions to the colder molecule. It's kind of random the way these things are moving, and random collisions will occur. So before you'll have a high temperature and a low temperature, and after, they're going to be both the same temperature. Now this is called heat. Heat is an energy transfer that occurs this way from a hot body to a cold body. That is the definition of heat. It's an energy transfer. So both of these things are processes, not properties. Both of them are things that happen. Now you can't measure how much work is in a jar, or you can't measure how much heat is in a jar, because it's something that happens. It's an event. It's a process, not a property. Now temperature is an example of a property. Temperature is something that you can dip a thermometer into this, and you can see what the average temperature is going to be. Now notice another thing about heat and work. In the end, you can't really tell what happened. Here the gas gets hotter, and here the gas gets hotter, but they were caused to warm up in a different way. Their temperature rise comes from a different source. So these two energy transfers can be looked at as a change in energy. Let's write this as an equation. The change in energy, I'm going to write this way with a delta. This Greek letter delta means change. Now, we've said that the total energy of the box can't change. That is, the hot gas and the cold gas, if you add their energies together, that's the same total energy that this has after I take the wall away. The total energy doesn't change. So when I talk about a change in energy, I'm only talking about a part of the box, maybe one object. And this delta is what I use as a symbol for change in. Here's what the delta means. If you take the final energy of the gas in the right chamber minus the initial energy, when I write delta E, that is an abbreviation for the final energy minus the initial energy. And we're going to use this a lot. We're going to use it for temperature changes. Delta T is a temperature change, and that means the final temperature minus the initial temperature. But how do I relate the change in energy to heat and work? The change in energy is going to be equal to the heat plus the work that happens. And I'm using symbols now for heat and work. We usually use a symbol Q for heat and a symbol W for work. Now in physics, they'll put a minus sign here because their point of view is a little different. I'm interested in the gas that's energy is changing. In physics, they're interested in what's happening outside the system here, outside the gas. They're interested in the motor or whatever that is pushing this piston in. And that's going to affect the way that they write signs down in some of these equations. But this is the way we write it in chemistry. This equation has a name. It is one form of the first law of thermodynamics. It has got, if you take the energy that is transferred as heat and add it to the energy that is transferred as work, those two will add up to your energy change. Sometimes you don't have both of these things going on. Remember, when we had work going on, we had to have an opposing force. We defined work as moving an object, pushing an object against an opposing force. So if you don't have an opposing force, or if you don't have motion, then the work will be zero. The change in energy will be equal to the heat when no work is being done. When you don't see any motion and you don't have an opposing force, no work is being done, and the W is, it drops out. It'll be zero. Now, what happens when no heat is being transferred? When you're only doing work, then you'll have delta E equals when no heat is transferred. When is no heat going to be transferred? Well, heat needs a temperature change. So these are both special cases of the first law of thermodynamics. When you have no work, the work is zero, and the energy change can be measured by measuring the heat. When you have no heat, no temperature change happens to your object that is undergoing the energy change, then the work is purely responsible for all of the energy change that you see. Now, in the next video, we're going to concentrate on this one here. We're not so interested in the work that's done in chemistry. Not right now, anyway. What we are very interested in are temperature changes. A lot of times, chemical reactions will be accompanied by a temperature change because there is an energy change going on. By measuring the temperature change, we're going to see where you can measure the heat and so the energy change.